if there's any question before I start, just let me know. I think everyone can unmute themselves. Just go ahead and ask. So what we did last time, right? So we finished with the proof of Kochie's theorem, right? And so let me just write Kochie's theorem in the formulation that we had it. Right, so we have that, so Kochie's general theorem, right? Kochie's theorem, right, was if f, right, f a region, right, analytic in a region omega, then the integral of gamma of f z dz, right, the integral over a curve was equal to 0 for all closed curves. Closed curves gamma such that gamma was homologous to 0 in the domain, right? It doesn't go around any loop that it doesn't go around any point outside of A, right? It doesn't go around any hole that A might have. Okay? And so basically we spent almost all of Tuesday, I guess, just proving this theorem, right? So we finished the proof of this. So now let's say that that this is not the case, right? So let's say that okay, so we want to understand curves that are not congruent to 0 mod omega. In particular, one implication of this theorem, right, is that if omega is simply connected, right, then every curve is homologous to 0, right? Simply connected is a set without any holes. So if the set that doesn't have any holes, then the curve can't go around any holes. And so if this is simply connected, then we just have that f of z dz is equal to 0 for all closed curves. Wait. Okay, and immediately this implies, this will imply right away, right? And this of course follows from above because every curve will be homologous to 0, and this implies, for example, Kochie's theorem on a disk, and so on. Okay. But now what happens if what happens, right? So what happens if omega isn't simply connected, right? So what do we have then, right? In particular, let's say that omega is like a region like this, maybe has a hole, another hole, another hole. Right, let's say that omega is this region. This is clearly not simply connected, right? It has 3 holes, right? It has, say, this green hole, right? The red hole, and say, let's see, do I have another color? Yeah, and the black hole. Okay, and so clearly this region isn't simply connected. What happens then? Of course, for curves that just maybe if omega is a curve, let me see again if I have. So if if the curve, right, if my curve gamma is just a curve that doesn't go around any loops, then it's fine because the curve is homologous to 0. But if I have a curve omega that goes around like this, then this is problematic, right? And we don't expect the integral necessarily to be 0, right? So the question is what happens then, right? And let's say that, and so let's talk about multiply connected regions. Okay, so let's talk about multiple or multiply connected regions. Okay, and let's say that, let's take omega, let's try to count the region. So one way to count the region is to look at omega complement, right, in the extended plane. Right, and saying that, let's say that omega complement has n components. Right? And in this case, it would be 4 components. We would have the unbounded component right here outside, and then you would have each one of the holes inside. Right? So let me erase maybe this one. Right? So this, in this case, they would have 4 components. Right? And let's say that A1 all the way through AN are the n components. Okay, and let's say AN is the unbounded one, right? The one that contains infinity. Say AN is the unbounded one. Right, n components, right, of the complement. Okay. Okay, so clearly, if, okay, we've seen theorems of this type, but let me reiterate this maybe, right? If there's a curve that is in omega, right, then of course, if I look at the winding number of the curve around a point A, this might not be 0 if A is inside one of these components, right? This we don't know if this is 0 or not. However, what we do know is that, right? So what we do know is that this is constant, right? It's constant within for A within one of the components. Right, so what do I mean by this? I mean, if say A1 and A2 belong to the same AK, then the winding number needs to be the same. Right, I mean, we've seen theorems of this type. Right, I mean, maybe we've seen versions of this where, right, so we've seen versions of this where right, so we said that we draw the curve and then we look at the regions that the curve determines, and then within those regions the winding number is 0, but because the connected component of the complement of omega is connected, it needs to be within one of these regions, right? It can't be in 2 of those regions because it doesn't intersect the curve, because it doesn't intersect omega, and so it needs to be within one of the regions. So for sure these winding numbers are constant. Okay, and clearly, right, and of course for the unbounded one it's 0, right? So, and if A is in the unbounded set or connected component of the complement of omega, then of course the winding number needs to be 0. Right, so let's look. All I'm saying is whatever curve I have, let's say that my curve goes like this maybe. Right, so this is my curve gamma, right? The winding number to a point outside, right? This is a point that's outside. Let me draw a line around the picture, right? The winding number is always 0. Any 2 points in the green place, the winding number is constant, right? Any 2 points here, the winding number can't have changed, right? Because it's always within the same region determined by one of the regions determined by omega, by the curve gamma, and right, that's all I'm writing here. Okay. So basically, by exactly the same argument that we did with, by the same argument that we used to prove that being simply connected was the same thing as winding. Like if your region, right? So we showed, maybe it's worth drawing another picture just to make sure that things are clear, right? So what we said is if we had a region maybe like this, say omega, right? And if it wasn't simply connected, where the definition was that the complement was disconnected, right? So the complement now has this region here and this region here, right? So it's disconnected. That there was a point outside the set where the winding number was not 0, right? Let's remember how we construct this, right? We took a point here, a point A, and then we did all these squares in which we basically built a little like square around this. Right, we did this construction where we built like something like this around here. We called this the curve, and we showed that the winding number of the curve connected to a point A, which is not inside omega, and the curve, of course, is inside omega, was 1. Right, so we showed that if the, basically, if the complement of omega had a connected component that wasn't the unbounded one, then we could create a curve whose winding number was 1 even. So in particular, it's easy to see, right, that that for each k, right, using exactly the same argument, it's easy to see that for each k in the setup above, right, there exists a point, there exists a curve, sorry, there exists a curve, say, let's call it gamma k, such that n gamma k a, right, is 1 if a is in AK and 0 in all of the other AJs, right? So, you know, and what is the picture to draw? It's the exact same picture, right? So think of this, and now maybe I have, you know, two holes, right? This is my hole A1, this is my hole A2, and this is my hole A3. We just have to carry the exact same argument in which we build this curve around here, right? And clearly, sorry that my drawing abilities are not great, right? But we build this curve around here. Clearly, the winding number around, you know, any point in A1 is 1, and everywhere else is 0. Okay? Because, I mean, it's constant within each region. So, okay. So then this, you know, we didn't prove that. I didn't just do all the full argument here, but the full argument is here. You just have to go back to the proof of Kochie's theorem. Okay, and so now let's say that, right? Let's now take a curve, right? So let's do this now. Now comes a very important idea, right? It will come sort of almost trivially, I would say. I mean, it doesn't feel like a complicated idea, but it's an extremely powerful idea. Okay, and so now is important, the idea that's about to show. So let's say that I have a curve that's inside my set omega. So it's any curve. Okay, maybe let me see if I can keep a picture, like a bit of a more interesting picture nearby. Let's say maybe. Yeah, maybe let's say this one. Okay, I should to be. Let's say I do like just to give an ordering. So this is, and let's say there's another hole. This is A3, and now I'm calling this one A4. Right. This is like erases way too much. Okay. Okay. This is my omega. Okay, so let's say this is my curve, right? So let's say I grab my curve, and now I say, well, you know, let's pick AK inside AK, right? Now this curve will have some winding number, right? Let's say this winding number is CK. Okay. Now this winding number is constant, right? So the winding number is constant within each region, right? It's the same, it's constant, right, within AK, right? And so if this is constant within AK, right, then the winding number of, okay, so let me maybe write the formula, right? So the winding number of the curve gamma around the point AK and around any point in the set AK is CK. So it means in particular that the winding number of gamma minus CK gamma K, right, around AK is 0 in AK, right? Remember how I constructed gamma K was the curve whose winding number around, right, was the curve whose winding number around AK was 1 and 0 everywhere else, right? And so if I now to my curve subtract CK gamma K, my winding number around AK is 0 because it was CK, and in the other one was CK times 1. And it didn't change on any of the other sets, right? And remember, around AN was 0 to start with. And so basically what this means, right, it's easy to see now. I'll write it and then maybe we can just discuss it to convince ourselves, right? That basically this curve, or let me write it in this language instead. If I subtract C1 gamma 1, I'm now have winding number 0 at A1, and the winding number didn't change on any of the other sets because gamma k has winding number 0 over any other for aj for any other j, right? So if I take now the subtract all of these, right, all the way to I guess n minus 1, because there's nothing interesting happening at an. Since it's the unbounded set, the winding numbers are always 0. Oh, sorry, this keeps. Okay, then this curve now has winding number 0 around any point outside of omega, right? Because if you look at a point outside of omega, it's in a certain k, and so in a certain k, this part will have a contribution ck, and then they will cancel that contribution in the term ck over in the sum. So this means that this is actually homologous to 0 in omega. Right? And so this means that, you know, the curve gamma is homologous to the curve C1 gamma 1 plus C2 gamma 2 plus so on plus Cn minus 1. Okay. So now from here we can draw a lot of conclusions. Okay, so let's take a second to sort of, you know. So someone asked, why can I take a curve? Okay, so I need to. So in order to do this, I'm thinking of curves as it's okay to take the integral over two curves. Say, you know, I can take the integral with. Yeah, so I'm defining the integral over curves as if I have two curves that are disconnected and I'm summing them, I do the integral over one and the integral of another, right? And as long as I have finite sums and so on, all these things are well defined. Right, I mean, maybe we could spend a bit of time trying to like actually argue that all of this is well defined to define the integral, but right, it's just, you know, it's there's a little bit of housekeeping that I'm not quite doing because I won't actually need this in any, you know, rigorous way, but you just define, I just define the integral over curves and, right, and the curve doesn't need to be continuous. As long as it's pointwise smooth, then everything is fine, right? So if I have the integral over, say, you know, like think of a curve gamma 1 and then a curve, you know, gamma 2 that's, okay, this needs to be smooth. And the curve gamma 2, the integral over the curve gamma 1 plus gamma 2 is just equal to, right? And I can define, right, in particular, then I have an algebraic structure over the curves and all this. And what I mean by multiplying a path with a constant, I mean just going over the path that many times. In particular, this constant better be integer, right? For now, at least. Right, they are integers. Because the winding numbers, I know they're integers, right? We proved that winding numbers are integers. And yeah, so I mean by taking, say, the integral, right? By taking twice gamma 1, I mean just go around gamma 1 twice. Okay, is there any more questions? Is this clear? All right, but thanks for the questions. Yeah, I mean, so let's see in this picture what one means, right? So what I mean here is that, okay, it's always hard to look at these pictures and try to make sense. So, right, what I'm saying is that this curve up to homology looks just like the curve where like maybe gamma 1 is this curve, and maybe gamma 2 is this one. Going like this, and is saying that, right, the curve gamma up to homology just looks just like gamma 1 minus gamma 2. Okay. Where, you know, in the sense of the integrals and the winding numbers and so on, because the winding numbers are just integrals. Okay, is this clear what is meant by this? Okay. So there's actually quite a bit that can be retrieved from here. Okay. One, which I will not talk about as much, is in a way the start of algebraic topology. right? Which is that clearly, you know, the curve, if I think of the set of closed curves, right, with certain smoothness or something, right, and I have this, so someone asked if I say plus or minus. Minus because the winding number of gamma around A2 goes the other way, right? And I draw an 8 figure, and so gamma goes around A2 clockwise, not counterclockwise, and so we get the minus, right? The winding number of, drawing pictures is always rough, but the winding number of this for a point A2 was -1, right? Because gamma is going around clockwise, so against the normal way that angles run. Okay, yeah, but thanks for the questions. This is a very fruitful idea in mathematics, and so yeah, I want it to be clear. Then how we'll use it to compute, it'll be more right. Once we are using it to computing, will be certainly a lot more concrete. But the idea itself is a very productive idea in mathematics and in topology and complex analysis and so on. So I just want the idea to be well motivated and clear. Okay, so from the side of algebraic topology, the observation to be made here is that if I think of the space of closed curves and I take it up to homology, right, with say the algebraic structure where now I can add, I can multiply by integers and so on, exactly in this structure, right, and then I take the quotient. But where with respect to homology, right? Just I mean, this is called mod just because it's very much like in number theory when you do things quotient by mod prime or an integer, right? So now, right, this is clearly very much like a basis, right? Where this right, this gamma 1 and gamma n, right, are what's called an homology basis. Right? So, right, are a basis of this space. And now I can start asking questions of, how many curves are there in the basis? How big is the basis, and so on. And I can use, right, and now I can use I can use theorems in linear algebra and algebra and so on to say that, say, the base is always of the same size. So there's a well-defined, notion of dimension here that, in this case, is just the number of holes, or the number of holes, and so now I can start given a region or even a space. If I define homology if I define homology not necessarily with winding numbers, but for higher dimensions with respect to curves being able to be contract to a point or not, right? I get for some topological space, a variety or a region on the complex plane, I get a notion of how many holes it is by looking at algebraic properties of the structure that is obtained by taking the set of curves and quotienting out by being homologous to 0. Okay? And so now you can do lots of things with this, right? You can try to understand this structure a lot better. You can try to understand, right? Like, you can try to understand this group a lot better. You can try to understand if you have two regions and if you can show that this algebraic structure is different between them, then they need to be different regions and they can't be mapped to one another with operations that preserve this structure and so on. And so it allows you to do a lot to study regions and topological varieties and so on. Okay? So this idea is extremely powerful in studying the topology of regions and of manifolds in general. Okay, so I won't get too much into algebraic topology, but I think you'll take topology next semester and you'll probably see versions of this then. Okay, so let's see. Let me see what, now I want to use it to compute. Let me just make sure I don't forget anything. Give me just 1 second. Okay, and now, yeah, I was wondering if I should say any words about cohomology and so on, but I think I will decide not to. Maybe I can chat a bit about this if there's any questions afterwards. Okay, so okay, so let's see what this can tell us for computing. okay, computing integrals and complex analysis, right? I now just tried to convince you that this is a powerful idea to learn about topological properties of the region and geometry and topology of spaces. And now let's see how what this can tell us about computing integrals. Okay? And so let's say that I have, let's go back to functions now. Let me go back to another color. Let's say that I have f in a region, right, analytic. Okay. Right, now clearly, if I take an integral around the curve of fz dz, right, because, because the curve gamma is homologous to the curve c1 gamma 1 plus c2 gamma 2 and so on, right, the integral of fz over the curve gamma will be the same as the integral over this other curve with the sum, right? So this will be the same as, let me write here maybe this way, right? C1 gamma 1 plus, okay? Where this is understood in taking the integrals of one at a time. So we'll do that in a second. Right? Why? Because of this above. Okay. Okay, so now okay, so what does this mean? Because of the integrals, this means I can take the sum, let's say here, okay, from 1 to n minus 1, right? And now I get, right, ck, the integral over gamma k, f z dz. Okay, and so the integral around, if my omega isn't simply connected, right? Again, not simply connected. And let's say finitely. Let me have them be finitely connected, multiple connected. Okay. Then the integral around a curve gamma is just given by the sum of these coefficients that depend on the curve, right? It's around how many times it goes around the hole, the kth hole, times an integral that's now fixed, doesn't depend on my curve, right? This no longer depends on gamma. So the dependency of an integral with respect to gamma is linear in a way, right? It depends only on linearly on this coefficient ck, right? I mean, that's where the this algebraic structure is coming from, right? And so let's call this the period of the function, right? So let's call this pk, right? So we call this the period of periods of f, period of f, right? Which is when I integrate, around a hole, how much do I get? Okay. And so in particular, the integrals around a curve are always integer multiples, an integer linear combination of the periods. Okay? And so now, because of this, what we now can do is just investigate what these periods are, and this will allow us to compute integrals of functions over curves in domains that are not simply connected. And in particular, it will allow us to compute integrals of functions over curves where the function might have a singularity inside the curve, right? All we have to understand is these periods. And it turns out that the period is basically what we'll call a residue. And this will give us the so-called calculus of residues, which is extremely useful to compute integrals. Because now, every time you want to compute integral around like a contour integral in a closed curve, all you have to compute are these periods, and which will correspond to residues, right? So this is what we're going to do in the next 15 minutes. But maybe before, just before we do this, let me just make a point, right? So clearly, the Kochie integral, the Kochie integral formula, which we'll use, works just the same for any, that we proved on the circle, on the disk, will work just the same because of Kochie's, theorem, because of our proof, will work exactly the same in any region when a curve homologous to 0, right? The proof is the same. So let me write that because we're going to need it. If f is analytic in a curve, in a region omega, then just Kochie integral formula now holds for f of a equals 1 over 2 pi I. Hopefully I won't get f 6c. Right, provided that a is not in the curve and the curve is homologous to 0. Right, exactly the same theorem as before. I mean, we did it for the disk, but it's now that we have general Kochie theorem, it comes straight away. The same exact argument. Okay, so let's say now, okay, now that I have this, because this will help me understand singularities. We'll see in a second. Let's say that. So right. We're gonna get what we want to do now in the next 10 minutes is do basically calculus of residues. I mean, we have everything. We just need to collect it. Okay. So let's say that f from omega to c is analytic, except in isolated singularities. Let's say finite, right? We've seen many arguments where we can go, once we fix the curve, then inside you can, right? You can make sure that they're finite. You can deal with these things, right? Even if they're infinite. But let's say they're finite, because the way to deal with infinite things is always the same, and we've done it a couple times. So let's say finite. Okay. Then right. So I mean, maybe I should say prime is analytic in omega, except in isolated singularities this, where clearly omega prime is now equal to omega take away the singularities. Okay, so let's see. So we have such a function. So of course, clearly, because they're isolated singularities for all, right? So what is the plan? Okay, maybe a picture. I shouldn't write too many equations without a picture. So what's going to happen, right? So I have a region omega, okay, and I have singularities a1, a2. What I'm going to want to do is describe what is the integral of a curve on this region, right? And the issue is that and I will want to do it for curves that are simply connected. There are curves that are homologous to 0. So let's just think now that omega is simply connected, right? But omega prime clearly is not simply connected, because it has these holes, a1, a2, a3. But now the integral of a curve gamma, right, will be given by linear combinations or integer linear combinations of the integrals around, these around curves that just go around one of the holes. And so what I have to create is these homology bases, right? And so what is the homology basis? I just have to create some curve that goes around this, right? Let's call this C1. Some curve that goes around this, let's call this C2. And some curve that goes around this, let's call this C3. Because now if I create such curves, the integral, right, because the function f is now analytic everywhere in omega except these 3 points, right? This is clearly an homology basis. And so if I take the integral of some curve, let's say I do this, and say this, I don't know, something like this, right? Curve gamma, then clearly the integral in gamma should be, okay, let me make sure I get this right. So I go around C1 one way. So it should be around the integral on C1. Then I go around C2. This is hard to, I go around C2 the opposite way. And I go around, C3 the right way, okay? Right, so clearly the integral of a curve is going to be given by a sums and differences of these integrals around this curve, right? So I want to create, the goal here now is to create an homology basis, right? Create homology basis. Okay, so now, right, so how do I do this? I just have to create the circles. Everything is done already in the picture, right? But let's do it. So right? So for all j, there clearly exists some delta j such that, the ball, say the closed ball of the closed ball centered at aj and with radius lambda j is inside omega prime. This is just a fancy way of writing for any one of these singularities. I can draw a ball around it that doesn't touch any of the other singularities. Right? That's all I'm saying. Okay. So now we just have to, right? We just have to make Cj be that curve, right? Cj is just the circle, right? It's just, I mean, I can call it just the boundary of that ball, right? Right. I should say, okay, maybe here, okay, to be, precise, I need to take aj because aj is not in omega prime. So to be completely precise, I should really write it this way, right? So basically, a circle around aj that that doesn't contain any other singularity. Okay. So, okay. So now what does this tell me, right? It tells me that the integral around gamma will be equal to the sum of the integer linear combination of the periods, right? So let's define the periods, right? So this will be a curve around Cj of f z dz, right? This will not depend on the circle I get, right? Exactly because any circle, like of course there's many choices of delta j, but all the corresponding circles are homologous, right? This we know. Okay, and so I define these periods. So what does this mean? Right, this means of course that, if I have a function, we'll get there, but if I have a function, a curve, an integral of a curve omega, it's going to be given by linear combinations of these quantities. Okay, but let's look at the period of the function, right? Let's look at what is the period of the function. So maybe okay, let me see if I can, before I do, I'm about to write some equations, but I don't want them to show up like it's, like they come from nowhere. Let me see if I can give an intuition of what we're about to do next. So before I do it, so what do we have? Let's all take a step back and think about what just happened and what's about to happen. So we have now that the integral around a curve gamma will be given by a linear combination of these periods. So if we want to compute the integral around gamma, we just need to understand what these periods are. So what we want is now machinery, right? So the goal is now some kind of machinery to compute these periods, right? So the goal, right? We should always keep an eye on, what's our goal. So you want to, some machinery to compute, right, these periods. Because once we compute that, we can compute any integral. But it's not obvious at all how to compute such a thing for now, right? So this is what we want to develop, machinery to do this, right? That's the goal. What is one function that we can compute the period of, and it's an interesting period, right? Is if the function is f of z is equal to 1 over z minus aj. This is something that we've done, a few times. In particular, the integral over cj of 1 over z minus aj dz, we know is equal to 2 pi I. Okay? And so there is one function we can compute the period of, and has an interesting one, right? It's not 0. Okay? Now, maybe to, trying to convince you that this is actually more than just a function. If you think that if you go back to when we studied poles and functions basically responding to polynomials, right? And functions that had singularities basically corresponded to polynomials and polynomials of 1 over z or 1 over z minus the singularity. And so you can imagine that f of z around aj will look like different sums of different powers of z minus aj. But all the other powers will have integral 0, right? We've seen this too, right? 1, because if it's a positive power of z minus aj, will just be analytic. And even if it's a negative power, as long as it's not the power minus 1, then it has, we saw that it's the derivative of a function, and so it was okay. So in a way, the only part of the function, right? The only part of the function, if you think of a function that is an isolate, that whose singularity is a pole, the only part of a function that won't have a 0 period is exactly this part of the order minus 1, the degree minus 1 part of the pole or of the polynomial. Okay. So this means that basically by understanding this period, we can understand the period of any function at a pole. Okay, that's what's about to happen, and so I will do it now. And so let's define. Okay, so let's define the residue, right, motivated by this as the period over 2 pi I, right? Because I want the residue of this 1 over z minus aj to be 1. Okay, and so let's define this. Let's do a definition. Okay. Okay, maybe before I do the definition, I should say that if we define this way, right, then clearly if I have the integral over over the curve Cj of f of z minus rj z minus aj dz, this is 0, right? Because the left term is equal to pj, and the right term is equal to rj times 2 pi I, and this is exactly the same by the definition of rj, right? So this is 0, and so I can have a definition in which I say the residue, okay, the residue of f at an isolated singularity aj is the number, or the complex, is the number, my pen is, I guess, the complex number rj such that fz minus rj z minus aj is an integral 0 for any curve in there, right? So in other words, has a derivative in the punctured annulus. It is a derivative. Let's see. Not as a derivative, as a primitive, of course, right? Because the integral is 0. So is the derivative of an analytic function in the punctured sorry, in a punctured disk. Okay, so because we're out of time, I'm not going to actually, tell you how to compute these things. But let me just say in the last, just take an extra minute. So I define the number rj such that the integral around the point cj is 0. Okay, so in any curve, any closed curve in that small neighborhood, in that ball, will be 0, and so we know that it must be this function must be the derivative of an analytic function. So now I define rj exactly this way. Okay, and now the point is that once we know what the residues are for the function, we're going to be able to compute any integral. The thing that is not obvious at all now, right? So there's two reasons for this to be useful, right? Is once we know the residues, then we can compute any integral. I mean, let me just say any. I mean, essentially any integral. Maybe we can compute integrals. And two, residues will be easy to compute many times. And that's not obvious at all yet. Right? The reason why they're going to be easy to compute is that they basically correspond to the term, right? If you have a pole, they'll basically correspond to the term that, like if you expand in the way that we expand, like the Taylor expansion, but on the variable 1 over z minus aj, right? Or, I mean, the way you should do this is if you have a pole of degree h, you multiply by z minus aj to the h, and then you do Taylor there. And there is one term that corresponds exactly to 1 over z minus aj. The coefficient of that will be the residue. And this is something that, sounds complicated, but one can actually compute for functions rather easily. And once you know the residue, you know the integrals. So we're going to do all of this on Tuesday, and then get something called the argument principle. And yeah, so we'll see how we can actually use this to compute integrals. But the point is that this idea that, if I have a curve, I can decompose it into, say, these n-1 curves corresponding to this homology basis, sort of lets you understand a lot about the regions, and this is, gives you algebraic topology and so on. And it lets you also compute integrals, and this is really what helps to compute counter integrals and so on. You'll see this on Tuesday and in the exercise class. Okay, sorry for taking 2 or 3 extra minutes.